We're in the last round of this month, which will be more focusing in the quantum aspect. As you see, some of the talks, mini courses will be, in fact, the mini courses will be online, and some of the talks too. The first speaker in the morning will be Mario Szegedy from Rutgers University. You can hear us.
Yeah, I can hear you.
Everything fine there? By the way,
yeah,
good morning from Montreal.
It's a pleasure for me to speak at University of Montreal. I have dear friends like Pierre Mackenzie there, and so the university is close to my heart. Do you hear me well?
Yes.
Okay. And so the audience knows quantum or more like mathematicians?
Both of them, I think so.
Okay, so what I'm going to talk about is like a result in the making that we will submit to QIP 2023. It's a certain subset of the things that we have done, and I just picked this subset. So the work is joint with Sergey Bravyi, a student of mine, Sharma, and Ronald. So the problem is EPR pair generation when you have a state that is shared with n parties. So in the introduction, I will just focus on 3-4 parties, just so you see the model. And so we want to generate, like then a referee comes and tells that between which parties we have to create the EPR pairs. So if we just want to create one EPR pair, then the resource state, which is an EPR pair itself, would be obviously sufficient. But so now we are interested in resource states from which we can generate like EPR pairs between arbitrary parties. Now such a resource state, so let's assume now we have 3 parties, and such a resource state is the GHZ3 state, which is like for the non-quantum audience is the 000 plus 111 state. Okay, so I wrote it as a question, like, can we generate an EPR pair between Alice and Bob in such a way that after we do the operations, that pair will be disentangled from Charlie, because like we want these EPR pairs for later for, let's say, teleportation, so we don't want the EPR pair to be entangled with anything. So the answer is yes. Okay, so the original resource is a state, an entangled state between the parties. So in this case, the GHZ3 state, and so what the algorithm that is allowed to be done on this state is that the parties cannot do joint operations. So they can send classical bits, or they can just do operations locally on their own side. So this is local plus classical. So this is a famous model called LOCC. So these two kinds of operations are allowed. Okay, so here is how you generate an EPR pair from GHZ3 for Alice and Bob. So first Charlie measures his bit, and it matters in which basis. So not in the standard basis, but rather in the plus minus basis. And if the result is plus, then it's easy to compute, and then Alice holds the 00 plus 11 state. And if the result is minus, then Alice and Bob actually hold the 0, 0, minus 1, 1, which is not quite an EPR pair, but since classical communication is allowed, Charlie can just tell whether his measurement was plus or minus, and in the case it was minus, so he just conveys this information to Alice and Bob, and then they can just adjust in a simple way. For instance, Alice performs a Z gate on her bit, and the 0, 0, minus 1, 1 becomes 0, 0, plus 1, 1. So that's our first example to an LOCC operation. So you see that no two parties jointly performed any quantum operation. Since the GHZ3 state is completely symmetrical, then of course from the very same GHZ3 state, if necessary, like with the LOCC, we can create also EPR pairs between Alice and Charlie or Bob and Charlie. So this resource allows us to create all these three possible EPR pairs. So now let's go one step further. So if we have like a GHZN state, which is just very similar, so it's a straightforward generalization of GHZ3 state, then we can create an EPR pair for between like any two selected parties. So notice that the starting state, we don't change, but the algorithm, like, so the referee tells which two parties need to get an EPR pair, and from this very same state, then just the parties can act in an LOCC manner and produce that EPR pair. So how about if we want now two EPR pairs, so now the referee actually tells a whole pairing between Alice, Bob, Cecil, and Dora. So can we find a resource state such that we can go LOCC manner from psi and create all these three, either of these three possibilities? And the answer is no, because if we could do that, for instance, if from psi we could go between Alice, Bob, and Cecil and Dora EPR pairs, and we could also alternatively, we could do the ACBD, then we could also go with LOCC from the ABCD into ACBD, because we didn't do any measurements, so all our operations are reversible. So if we can go from phi to the first one, and we can go to from phi to the second one, then we can also go from the first one to the second one. Now you see the impossibility, because in the first state that we created, it's a tensor product of AB EPR and CD EPR. So AB and CD are completely disentangled. But then with LOCC, we can never create new entanglement, like we cannot create entanglement now between A and C. So that's the fundamentum of quantum, that entanglement can be created only with joint operations. So once you have entanglement, you can cleverly exploit that, but to create entanglement, you need to perform joint operations. So there is a no-go for four parties when we want these all three possible pairings. So it's not the end of the story, because so now we change the setting a little bit. and we also add help bits to the parties. So now each party, besides this output bit, which are the endpoints of the EPR pair, so I denoted them by PI, we also have working or help bits. It used to be called ancilla bits, but the new word is like help bits. So the bits P1, PM, P1. So for P1, P1I, PMI don't play any role in the output. So these are just working bits. But importantly, now the original resource is bigger, because the original resource is an entanglement, and now we have a bigger entanglement, because the working bits can be also entangled with each other for each parties. From this bigger entanglement, we want to distill, so to speak, all these EPR pairs. So let's see. So actually there is a simple solution, and it's a simple-minded kind of stupid solution. But so if our original resource is just a bunch of, like a tensor product of bunch of EPR pairs, then we can just always find the right EPR pairs, the right two EPR pairs. Like for instance, Alice, Bob, and Cecil, Dora. We can of course find these two EPR pairs. Okay, they might not be on the output bits, but then locally we can just swap the qubits around so that they will be on the output bit, which, like this picture indicates. And of course, whatever pairing the referee gives, like these three possible pairings, of course, they all can be implemented. So this stupid solution requires like two help bits. And so if we have, like, in general, for n parties, if we want like all pairings, like the referee just can give an arbitrary pairing between n parties, then a similar solution would require like n minus 1 or n minus 1, why not n minus 2 help bits. Okay, so there's just too many help bits per party, and we are interested in minimizing the number of help bits. And so that's going to be our task today, to create an original entanglement between n parties with m help bits, such that with LOCC we can create all possible pairings. So we want to minimize m. And we have said that m equals n minus 2 is sufficient, but in fact, m equals log n-ish is already sufficient. So that's our goal today, but it's not really what we are doing today, but we are giving a lower bound. We have upper bounds, lower bounds, we have other problems. So again, we have selected a subset of an ongoing work. So let me just give some notations. So n, let be an even integer, even just so that we can do pairing. And so an EPR pair is a plus state. And so if the case pair is ikjk, then it's the EPR pair is plus ikjk, and the state we want to arrive at, which we call pi, so this target state pi is just the tensor product of these EPR pairs. And so the referee just gives us pi, and then the players from the initial entanglement resource have to create that with LOCC. Okay, and so now let me tell you the theorem. So suppose that psi is a fixed state of n times 1 plus m qubits shared by n players, such that each player holds 1 plus m qubits of psi. And so this 1 plus m is one output bit and m help bits. So each party has 1 plus m bits. Suppose that for any pairing pi of n qubits, a transformation psi to pi is realizable by an LOCC protocol, such that at the end of the protocol, the ith qubit of pi is the output qubit of the ith player for all I. So this pi appears in the very end, disentangled from the help bits. So then m must be at least log n. So we give a log n lower bound on m. So at this stage, let me just check the time. Great. So I have 27 minutes. Okay, so here is the proof idea. So when usually in complexity theory, you give like a proof that something is not possible with a certain kind of computation, then you need two things. You need to understand what the computation accomplishes in k-step or what the computation can accomplish with the allowed resources. So we want to understand that mathematically. That's one side of the coin. The other side of the coin is to understand whether the task can confines to that mathematical condition which the algorithm can create when it uses the allowed resources. So what can an LOCC protocol do as described? So we have n parties so only classical communication and local operations are allowed. So here is the observation that an LOCC protocol can be always described by a quantum CPTP map, a completely positive trace preserving map. Now you don't have to be afraid if you are non-quantum, because really I will not use that. So I will tell you what I use, and what I use is just ridiculously nothing. But what is important here, though, is that these operators, so the actual big operator with which I am operating on the entire n-party system, because it's local, because it's LOCC, it decomposes into the tensor product of what the local parties are doing. And so this decomposition is important here. So you can forget a little bit about CPTP, and you can just think of that you have some linear operator that we are performing on the original resource state psi. And importantly, this linear operator decomposes as a into a tensor product of n linear operators. And so after we do that, then psi is gonna turn into the state pi which we wanted. Now what is going to be our resource? We are going to look at, okay, so this is how the proof idea continues. is we are looking at like, so what such a tensor product of linear operators, like what is the range of those things that it can be done? Namely, we are just calculating the dimension of this tensor product operator. And so what we have to notice, and so what I'm saying is that, you know, we don't, for a particular pi, we have the k1 pi, k2 pi, kn pi. So for a different pi, we have another k1 pi prime, k2 pi prime, kn pi prime. But so for all pi's, the k pi, the operator which accomplishes of going from psi to the state pi is going to look like this. So now we are just calculating the dimension of all the vectors, of the dimension of all the operators. So the operators form a linear space. So the dimension of this linear space, which looks like this, and so the punchline of the proof is going to be that this dimension is not sufficiently large for preparing for the referees, for all requests of the referees, because for all pi's, our method should look like this tensor product, but this tensor product can only create operators in a certain operator space of a certain dimension, and simply the variety of outputs that we must see for different pi's is going to be larger. So so that's what we are going to formalize, and so so the effort from now on is just formalizing this idea. And so now, okay, so the for when pi ranges in all pairings, then this state pi, well, it ranges with certain tensor product of EPR pairs, but sadly, if we just look at pi as is, then of course the pi is just sitting in an n qubit state because we have n output qubits. So the dimension is 2 to the n. And if you look at the details, of course, you have to look at the details, that this 2 to the n will never give you a contradiction, because the k as is also has dimension, is sitting in an operator space of dimension constant to the n and larger than 2 to the n. So you will never get a contradiction. But here is the trick, that so now we are taking not pi's themselves when pi is an n-qubit pairing, but rather we tensor up pi to a certain tensor power r, and we are taking the space which is spanned by those pi tensor r's. Now you are saying, okay, so do we gain anything by that? Well, yes, because, you know, even if we have a bunch of vectors that are sitting in a two-dimensional space, if like, let's say n vector, and later I will have a slide to explain that example, then, you know, when you tensor up each of those vectors r-fold, then these n vectors will all of a sudden sit in a, well, they span a larger dimensional space. So the pi's, actually, how many pi's do we have? Well, I give you the formula, well, later, but it's roughly 2 to the n log n, so rather than 2 to the n, so there is this log n, which this extra log n in the exponent, which so it's basically like n factorial. rather than just 2 to the n. So this extra log n will make the trick. So we have more pi's, and if we tensor up, then this log n kicks in. In any case, so the gist of the argument is that then that tensored up vector should sit in this operator space. So we also tensor up the operator space by R4. But the thing is, since the operator is local, then the tensor power, the R's power will just not grow as quickly as the dimension of pi, and that's what we exploit. Okay, so you will see the numbers. Let me now just tell you why. Okay, so first, so there are these two dimensions that we have to compare. One is that of like all possible pi's where they are sitting, or pi to the r's, and the other is all possible k to the r's. Now here is the mathematical essence of why the dimension of k to the r is small. Because so k to the r is okay, so what we are interested in is k psi to the r, but it's nothing else but k to the r applied on psi to the r, but psi was the original resource state which was fixed in the beginning of the algorithm, so the psi to the r is 6. So really the question is the k tensor r, what is the dimension of that? And so if now you write it out, then what's a crucial observation is that it has like r times n components, and so grouped by like n, grouped by n r, I mean by r fold products of like kr and k1 and then k2 and then kn. But the point is that this is symmetrical. So k1 tensor k1 tensor k1. So if you write it out, it's gonna be symmetrical. And so the R4 symmetric powers of operators that take m+1 bits to 1 bit, because that's what the ki does. So it lies in a space of dimension d plus r minus 1, choose d minus 1, where d is 2 to the m plus 1. So m plus 1 is just the number of qubits from which the operator takes the state, and plus 1, the 1 is the dimension of state where it takes that bit. So this is the dimension of this operator. I mean, I should say the space of all possible operators that look like this, that are generated by, for instance, k1 tensor k1 tensor k1. So when I let k1 range among all operators that take m+1 bits to 1 bit, so I take that set of symmetric tensor products and I see the dimension of the space that these generate, then this is the dimension. And so here a huge gain occurs, because if it was not a symmetric power but just a normal power, then it would be I guess it would be 2 to the d 2 to the d times r. But here yeah, sorry, go ahead. But here, so we have this mathematical gain simply, and so then d plus r minus 1, choose d minus 1, is less or equal than 2r, choose d minus 1, which is just 2r to the d. And again, so 2 to the d times r would be the non-symmetric case. And so you see here the 2 to the d times log r. And so that log r instead of r will do the trick. So the dimension, therefore, is pretty small. So 2 to the 100d times log n, which is like 2 to the log n, I mean, it's upper bounded by 2 to the log n to the 0.1 instead of 2 to the log n. So there is this 0.1 here, which is relevant. And that's already, I said that if m was little order of log n, then 2 to the m would be 2 to the little order of log n, and this little order I just transformed into 0.1 because that's enough already. And you know, so it's like log n to the 0.1, so 2 to the log n to the 0.1. Okay, so that would be the dimension estimate. Now that's just one of the n components. This is one of the n local components. And so when that we have n components, so now it comes out that the entire MR would be 2 to the log n to the 0.1 n. To the log n to 0.1 times n. Is there any remark? Okay, if not, then, so it's just a calculation. I mean, you can just go through it. That's a trivial calculation, but the point is that 2 to the log n to the 0.1 times n is much, much less than n factorial. So, I mean, like any power, any constant power of sort of n factorial, you see. So, and this, you know, n for the n factorial formula, which is 2 to the n log n. So the point is that's where we gain. Okay, so now we estimated the dimension of MR, and I have 10 minutes. Excellent. So now the only thing what I need to estimate is the pi to the r. So what is the dimension where the pi to the r's sit? And maybe it should be like constant times log n, but in any case, so it's a log n-ish, so r should be set like log n-ish. Okay, so I always told you like how many pairings there are, but here is the exact formula, like it's, you know, between n parties, so how many ways can you pair n parties, like it's 2 to the theta n log n. Okay, so you say, oh, so we are done. Well, we are not quite done, because like if we set r to be 1, then even though we have so many pi vectors, they are just sitting in an n-qubit state, as I have already told you, which has just dimension 2 to the n. So that's why we needed the r trick in order to make these vectors really independent. So when we tensor up, they become independent. So the question is that when r becomes log n-ish, then do we really get like n 2 to the n log n independent vector out of this system? And so I just give you an example so that you have an intuition what happens when we tensor up vectors. Like you see that for instance, if I have n vectors like 1, 1, 2, 1, 3, 1, n 1, like these are two-dimensional vectors, like they are all sitting in a two-dimensional space, so their dimension is just 2. But when I start to tensor up these vectors, like I take v1 to the third power, v2 to the third tensor power, and so forth, then all of a sudden I get, so I just drew, because you can imagine them, these vectors, these tensor power vectors over the nodes of a hypercube. So you see that these are your vectors, and then for 3 you already get at least 4 linearly independent when n is greater than greater or equal than 4 linearly independent vectors and so forth. So in general, the S tensor power like grows. And of course, so another example, which is more relevant to our example, is the case of unit vectors. When we have a bunch of different unit vectors in any dimensional space, in 2-dimensional space or any dimensional space, and we start to take the r's power of these unit vectors, then they start to become more and more orthogonal just because the r's power of the scalar product behaves as it behaves, as you well know. It's just the r's power of the tensor product, of the scalar product. So because of this orthogonality, when they are orthogonal enough, then they become independent. So a large enough power of any different set of different unit vector eventually, for a large tensor power, become independent. So and the situation is even better when the vectors are, to start with, are pretty orthogonal to each other. And so that's what we are exploiting here, that so we have two pairings, pi and rho, and then the corresponding quantum states, because the pairings are just the combinatorial pairings, but the state pi is the pairing, is the EPR pairs made from the pairing pi, and so the rho is likewise. So then their inner product is actually 2 to the minus n over 2, which is like exponentially small, but there is this k. So what is this k? Well, this k is just the number of cycles in pi union rho. But now think about that. If you take two permutations, then typically the number of cycles that they jointly form is not going to be that large. I mean, it's gonna be a small constant times n. So you still end up with an exponentially small inner product. But you need super exponentially small inner product to be orthogonal enough to form an orthogonal system. Namely, this super means you need an extra log n factor, so the r should be log n, and here kicks in the log n idea. So the r equals log n. Now, in order to, let me just see, I have 5 minutes, that's excellent, I have 2 more slides. So what I show is that we can, so first of all, among all pairings, you can still find 2 to the theta n log n of them that are pairwise, like the inner product is exponentially small. Equivalently, they like any two of those permutations don't form like a large number of cycles. By the way, if the two permutations form as many cycles as possible, then they are the same, because then they just form a bunch of 2 cycles. And then correspondingly, the inner product is depressingly large, like it's 1. But when the 2 permutations are independent, then they don't form that many cycles. So, so all in all, okay, so here is the combinatorial idea. I mean, it's just really like an execution of this idea for a combinatorialist. Like if you take, like if I just decompose n into 2 equal size subsets, like n over 2 just for the calculation, and I just take all those matchings between n over 2 and n over 2, then so what happens is, so let me just, that's the last slide. Then, so that's A and B. So two such pairings, well, of course, you can easily see what, so they form just a union of cycles. And then you can create a huge graph. So you have n over 2 factorial such matchings between A and B. And so now I'm just focusing on these pairings. There are also other pairings where pairs go between A or between B, but I don't care about them. I'm generous because I can afford it. And so now there is the red matching, the blue matching, the green matching. So I form like a huge graph from all these matchings, and I connect two matchings if they jointly don't have that many cycles. And this graph is going to be sparse, and therefore it will have a large independent set, large enough so the calculations just come out right. And so that large actually means 2 to the theta n log n, large independent set. So still I am not losing in the exponent more than a constant factor, and I am already completely independent. So the inner products are already exponentially small. And so that's when I am hitting it with the R, with the log n, then they are just going to be, the inner products are just going to be so small that they are all going to be orthogonal. And basically that's the end of the story, because then I just get that, so the possible outputs are, the dimension is just so large that my algorithm just cannot capture all of them because of the aforementioned argument. So thank you very much. Again, it was a pleasure to be in the University of Montreal, even though only virtually.
Thank you. Thank you for your nice talk, Mario. And let's see if we have any question or remark.
Very, very basic question. I'm just trying to understand your. Hi, thanks for the talk. I'm very basic question. I'm just trying to understand your initial hypothesis. So if A, B, C, and D share a G8Z state, they can build an EPR pair between A and B. If they share another G8Z,
or B and C, or
yes.
C and D, yeah.
Yeah, if they share another G8Z state, they can build an EPR pair between C and D. So if they have both of these states, if they have the tensor product of these states, they can build this A, B, C, D pairing. So there's a hypothesis about your psi in your theorem that I don't understand.
Yeah. So this is an excellent observation. So if I had n of such EPR pairs, or n over 2, then I could, a tensor product of n over 2 such GHZ states, a tensor product of many enough GHZ states, then I could have all possible pairings. But notice that such a tensor product, for this you would need n help bits, or n over 2 help bits, and that's just too many. So the goal is to reduce the number of help bits.
Okay, so the no-go theorem had what hypothesis about the shared resource psi?
Yeah, so the no-go theorem referred to 0 help bit. Well, okay. So the first for 4, there was 0 help bits, and the big theorem is with log n help bits.
Okay, and this strategy would require a linear number of help bits, right?
Yeah, so this strategy that you described would require a linear number of help bits. So,
thank you.
And we can actually do much better for that matter. So in reality, we can do much better. Mm-hmm. So your construction is good, but it's too many help bits.
Not sharp. Any other question?
Yeah, I have a question. So thank you for the talk. Now, so you started with the CPTP map. So that has a class operator decomposition. So are you using all of the operators in your protocol? Okay, I'm not sure about the dimension, the K1, K2.
So what do you mean whether I'm using all the operators?
Yeah, so given a CPTP
so
map,
since it's local, then this trace preserving Toy positive map should be a tensor product of local such maps. And so what the dimension I am computing is the dimension of the space in which all such possible maps are sitting. So the dimension is the dimension of the space for all the maps. It's not the dimension for all the vectors. That's another thing, that when I am hitting that space with a fixed vector, then I am just getting the output vector. But I'm not sure I understand your question. So what do you mean I'm using all the... I guess the answer is yes.
What does the index K1, K2, K3 refer to?
That we have n parties.
Okay.
So the index refers to, so each local, so the Ki is the map of the local, the i's party. So there is this big trace preserver, local, completely positive. So this map, this big one, and so the big, because it's LOCC, it decomposes into this tensor product. The number of tensor components is the number of parties, and so Ki refers to the i's party. And so that's the thing, that so this whole map is very limited because you are not allowed to do joint operation between the parties. And so locally, however, this map does not have that much variety. And so that's the limitation of such an LOCC algorithm.
Well, thank you. Thank you for the clarification.
Any other question?
Yes, so I have a question. Hi, Mario.
Hi, how are you doing?
I'm doing well. So nice result. Thank you. Nice talk.
Thank you.
I'm wondering, you've got this in a communication setting, if you like, but do you think the results will have implications, say, for in other settings, like measurement-based quantum computing, for example?
Yeah, when you say communication setting,
Sort of. I mean,
well,
because
sort
it's not
of. Well, you know,
multi-party.
it's like LOCC, like it's really
Mm.
LOCC. It's like no quantum communication at all.
Mm-hmm.
So there is the original resource, which creates the entanglement, but that's all the entanglement you have, like in the very beginning. And after that, but you are right, you are absolutely right that when like you are doing a measurement-based quantum computing, then you are creating all the entanglement that you will need later in the computation. I think that's right? You are creating it in the very beginning.
Yes,
and then
that's right.
So you are right that in a sense, it is reminiscent to measurement-based quantum computing. So I don't know how to exploit this reminiscence in order to give lower bounds for measurement-based quantum computing, but I think that's a good idea.
Okay, thank you.
Any other question? I have one. Bill's solution was not sharp, but how sharp is your result, Mario? But the Bill solution, Bill proposal was not sharp. This is what you said, I think. So how sharp is your result?
Can you get login helper qubits? Is that enough?
I am not sure I understand.
If your bound is sharp or not. I mean, if you can get, do you have a protocol exactly with this fitting with this bound?
Oh, sharp. You mean I understood shared.
Sharp.
Oh, sharp.
This
No,
is a
it is
Spanish
not
accent.
sharp because there is a gap between log n and log n. So it's not sharp.
Okay.
So yeah, that's a good question. No, it's not. But notice that our bound in the sense, it also lower bounds all sorts of protocols, like even even with post-selection, you cannot do better. So it's a weak. So the formula is smaller, but it applies to a wider range of protocols than what we are considering.
Thank you. Let's start again, Mario. Thank you, Mario. And now we go for, we have a break now. We have 20 minutes, more or less.